Hey, hey, my, rock and roll will never die. All right, we're going to do some RWOS problems where something actually rolls and something interesting happens when it rolls. And the classic one that we have to do is a round thing going down a ramp. Here's an incline. Here's a round thing. And we're going to release it from rest, and it's going to accelerate down the ramp. So, what is this round thing? What is the actual shape? Could be a sphere, could be a spherical shell, could be a solid sphere, could be a cylinder. The beautiful thing is I'm going to do a general solution where we don't care. And the way I'm going to do that is I'm going to say that this round thing, which has mass m and radius r, that will shock you, its rotational inertia is beta mr squared, where beta is called the rotational inertia parameter, which simply means it's whatever that fraction is that gets thrown in front of the mr squared depending on the geometry of the mass distribution. If it's a cylinder, it's 1/2 mr squared. If it's a spherical shell, it's 2/3. If it's a solid sphere, it's 2/5, etc., etc., etc. So this solution will be general for any round thing which is RWOSing down a ramp. Because that's exactly what this is going to do. It's going to RWOS down the ramp. The incline of the ramp is theta. Okay. Okay, what's the question? What do we want to know? We might want to know how fast it's going to the bottom of the ramp, but I'm sure. But so that means it's sweating all the way down. Accelerating. What's its acceleration? That's what we're going to find out. Yeah. What's its acceleration? Does anyone know? Come on. Yes, you do. Come on. We just did this. What's the answer going to be? Net force over modified M. The beta thing. So what's the net force? mg sine theta. And this is tricky. We're gonna this might be what will there be in the bottom, hiding in there somewhere? A beta. There's definitely going to be a beta. Say it louder, prouder.
I don't know.
Louder, prouder.
I didn't know what I was saying. I was just saying things.
Okay, fine. All right.
What do you want me to say?
So what you just said.
It's like 1 plus beta times, or like it's like m beta because you have the r.
1 plus beta times what?
I don't know.
Okay, we'll hold that thought.
Then the m goes out of it.
Oh, the m does go away.
That doesn't make the m's supposed to go away.
I actually don't know.
So now it doesn't.
Really good.
The answer G
Because it's like
5 over 1 plus beta.
Well, where phi is theta.
I don't look up the answer.
Because the r's would.
Okay, let's see what we get. So now let's do the problem and see what we get. But it's always fun if you know the answer before you start. If you do your thinking before you start, it might help guide how you do the problem. Yeah. Okay. So now let's find the acceleration by doing this as a dynamics problem. And if we do this as a dynamics problem, it means we have to start with it. Oh, I've lost my picture behind my recording thing, but I can move that. Whee! All right, so there's my picture. So I need to, if I can do dynamics, I need to start with a what of that round thing. Starts with F, rhymes with blubda. Good for you. All right, and this is not completely trivial.
We're answering questions, but I don't think that the microphone should hear us correctly.
Hello! So, well, people are just going to have to deal with that. Okay, a fubda of this round thing.
It doesn't sound like you're talking to yourself.
We'll find out. I might be.
It needs to be really loud.
So, okay, I don't know why I do that. So, because I get paid to do that. All right, a foot of this round thinga. Give me forces. Okay, start with the non-contact.
Do we need to set up a coordinate system first?
Hell no. No, the forces don't care what the coordinate system is. How we componentize them might care how the coordinate system is, but the forces don't care. So, I start with mode. Where now, because this thing is going to be angularly accelerating, it's important that we draw the forces where they act. Where does gravity act? Incorrect. On every bit of mass is where gravity acts. Every bit of the Earth attracts every bit of this round thing, but we can treat it as if it acts at the center mass. Yeah. Okay. I hate it when you're right and I say you're wrong and you end up being right. So this is mg. All right. No more non-contacts because there's no huge magnet at the top of the blah, 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 blah. Okay, so what's touching? The ramp, which means that we definitely have and maybe have. What do we definitely have? Normal force, which is acting where? At the point of contact, which is here-ish. This is the ramp. I'll draw a sketch of the ramp here. That's the ramp. So the normal force, and the normal force acts in what direction? Perpendicular to the ramp, which means that it goes radially, if you will, right through the middle, even though my arrow didn't quite hit it. This is my normal force exerted by the ramp, and it goes right through the middle of the round thing, because the round thing has round symmetry. Because after all, it's round. Yo, sup?
Can you draw the tip of the arrow as a point of contact so that the stem is at the bottom?
No. You're suggesting that we draw it this way. No. Because I just don't usually. I'm not used to seeing it that way. So you can't. You asked. I said no. I don't care. All right.
Very finicky.
All right. So definitely normal. Maybe what? Maybe friction. Is there friction?
RWOS, no. Yes? Static.
There could be.
Static.
Is there static? And I suggest to you there has to be. If there isn't, it wouldn't roll. Okay? And in fact, you might be able to imagine if this round thing were on a perfectly frictionless ramp, and you release it on a perfectly frictionless ramp, a round thing on a perfectly frictionless ramp would do the following. Here is the ramp. Here is the round thing, and I put a line in it as a reference so you can tell whether or not it's rolling, and it's already grouped. And so if this were on a perfectly frictionless ramp, it would just simply... Would it roll or would it just slide? This is JFS. Just break a slide. I'm sorry. And because why wouldn't it roll? All is going at the same speed, but there would be nothing to make it roll. Because in fact, what it does is, oh, I can't make this roll. Oh, can I? Okay, I can't do that and translate at the same time. Oh, I really can't. Okay. So, okay. So here's the thing. If it RWOS is down a ramp and it's going faster and faster and faster, that means the wheel has an
Acceleration.
what kind of acceleration? Angular and translational, because it is rotating faster and faster and faster. If I look purely at the rotation of this thing, it's going faster and faster and faster and faster and faster and faster. And, oh, don't do that. And because it's rolling faster and faster, and so if it has an angular acceleration, there must be a what on it?
Force.
What kind of force? Don't say force. Not what kind of force. Not what kind of force. Unbalanced torque. There's got to be an unbalanced torque on it. Does either of these forces create a torque about the center mass of this round thing? Starts with N, rhymes with go. They don't. So, and so that's another reason that we have to have friction. That's why it is if it's frictionless, what?
Nacho. Starts with N. Rhymes with go.
Nacho doesn't rhyme with go. Rhymes with gacho. Gacho, kind of. Sort of. Are there different degrees of rhyming? Oh, jeez. Nachos and Pop-Tarts. How about a Pop-Tart nacho? How about nacho cheese on Pop-Tarts?
I could do it.
I know you could. All right. So. What we now have two reasons to understand that there has to be friction. Friction, if it were frictionless, it would just slide and go faster and faster because it's on a frictionless surface. And also the friction force creates the torque that makes it roll, makes it angularly accelerate. So the friction force is what flavor of friction, static or kinetic?
Static.
Because it's RWOSing, it's not slipping. And what is the direction of said static friction?
Parallel to the
Yeah, parallel, but uphill or downhill. It's what prevents it from slipping. Here's my static friction. If it were not there, it would slip downhill. So the static friction prevents that slipping from happening. There is our completed fubda of the RWOSing round thing down an incline. You bet wow. Okay. So now we need a coordinate system. Coordinate system, which way is it accelerating? Downhill, so let's put our coordinate system in that direction, x, y, and so which force do we have to componentate? Mug. And we got our very familiar, I believe, mug, sine, theta, and mug, cos, theta, and our original mug goes by because we had now componentated it. Okie dokie. Karaoke. We ready to write some equations? Let's write some equations. Let's do a net f. I don't know which one. X or y? Y. We'll do y first. Get it over. Y. Yeah. Y.
Why?
Y. Well, we need y
Yes.
for friction, maybe.
Yeah, for the normal force.
For the normal force, because we need normal force in the friction equation.
Yep.
What's the friction equation?
Less than or equal to.
Ah! Less than or equal to. Static friction, nice, is less than or equal to mu times the normal force. When is it equal to? Jats. When it's just about to slip. Is this just about to slip? It's rolling without slipping. Were we told that this is the steepest possible incline it could RWOS down before it starts to RWOS? RWOS is rolling with slipping. And I will illustrate to you in real life, which means the people who are listening to this video on the interwebs will not be able to see this. Too bad! Okay, so if I have an incline, which is at a moderate angle, okay, if this round thing RWOSes, but if I go steeper and steeper and steeper, it still RWOSes. But I get to a point, that was me breaking things. Losing it.
Oh,
I got it.
under the middle table.
Or the mouse.
Hey, look at Charlie.
He found the mass. He's going for round two.
Okay.
Race the angle.
So now listen carefully. Can you hear it slip as it goes down? Probably not. Let's pretend that you can. But do you get the idea that I can get an angle here that's steep enough that as it goes down, and if you were to film it in high-speed video, you would see that it's not RWOSing, it's actually slipping, but it is also starting to roll faster and faster. That'd be an interesting thing to film in high-speed video. Maybe someday we will. Classic, maybe someday. So love when an adult says maybe someday.
Write it down.
And then
Yeah, it never happened. It never happened. So, when would you write that equation as an equality when you know you're at the angle of incline where it's just about to start slipping as it rolls? Were we told that in this problem? We were not. We were not told that it were at the steepest possible. We're just at some pathetic lower angle where it's just RWOSing very happily. And so will we use that equation, friction force equals mu n?
No.
We will not use that equation because it's not an equation, it's an inequation. So, by the way, that will be a separate problem we will do at some point, which is at what angle does it barely RWOS without RWISing? What's that steepest angle? And it ain't tan theta equals mu. It's something different from that. Which it was for a block sliding. All right. So we will not use this as an equation, and it's true, but we're not going to use it. And so do we care about fun? And I don't think we're going to care about fun, so we're not going to do net f in the y because I don't care. If we ever need it, we can come back and do it. So let's do net f in the x. Net f in the x equals mod sine theta minus phys equals max. Okay. Yeah. And it should be frustrating not to sub something in for the static friction force. You're just not going to. We always do. We always sub in something for the static friction force, and you're just not going to. Too bad. What other equation am I going to write? What other dynamics equation am I going to write? What about torque? Net torque equals I alpha? U alpha. I cot. Net torque har equals I alpha. Okay. Then what do we have to do for that net torque thing? What does net torque mean? All the torques, the sum of all the torques. Not some of the torques, all the torques. And so which of these forces is creating a torque about the axis of rotation? Axis of rotation being the middow. So I'm not going to write this down because I'm lazy. Does mg create a torque about that point? Why not? It has no r. Remembering the definition of torque, your torque is r cross f, which is rf sine phi. Okay. The mg ain't got no r because it is acting at that axis point. Okay, does the normal force create a torque? Does it have an r? Well, you bet it has an r. Normal force acts here, and there's the center there. There's the r for the normal force. So for the normal force, Fn, the r looks like this. The normal force looks like that. So it does have an r. It does have an f. What's phi for the normal force? It's not 0. It's 180.
Oh, because they're in different directions.
They're in opposite directions. What's sine of 180? Zippity-doo-dah. So the normal force creates no torque because sine phi is arrow 0. So the whole thing is arrow 0. And so there ain't no torque created by the normal force. What about the static friction force? Does it create a torque? It better. Rf sine phi. Okay, for the static friction force, move. For the static friction force, here's the round thing. Here's R. Here's the static friction force. So the torque created by the static friction force is R phys, and what's phi? 90. There's phi. So phi is sine of 90 degrees, and what is sine of 90? Arrow 1. So, of the 3 torques I have, I only have one, and that is R phys. So I get R phys equals I. What's I?
2 fifths of r squared.
Beta. We don't know what this round thing is. Beta m r squared. And what's alpha? It's alpha. What else is alpha? Can I sub in something for alpha? A over r. How come? Which equation am I using? using alpha equals, I'm using A equals alpha times R, but which of those equations is it? This is the same series of three equations that we had with V equals omega R. They're just going to differentiate with respect to time. Which one is this?
Oh, now it fails.
Is it RWOSing?
Yes.
It's friggin' RWOSing. I just got paid to say it's friggin' RWOSing. That's kind of fun. It's RWOSing. This is the acceleration of the center mass is alpha times R the whole thing. It's rolling without slipping. And this is what we want. So it doesn't have a string tied to it and the wheel is stationary. It is rolling without slipping. And so, and what is this ACM? Well, we don't know that yet. Oh, well, maybe we do. Yes. Times m. Yeah, so it's the acceleration of the round thing. Okay, so I'm going to sub in, let's see, I was up here on this line, and I was writing RFS equals beta mr squared, which is I. And then I'm going to write alpha, but instead of alpha, I'm going to write A over R. Yeah, A is center mass, which is the A of the whole wheel, which is what we're looking for. This is my favorite equation, ever. What do all the R's do? Which leaves us with fuzz equals beta A M. Bam! Fuzz equals bam! I like that. So, Bama, yeah, Bama is very tempting, but it's more fun to say bam. Okay, so now what are we going to do? We're going to take that bam and sub it back into this bad boy, but we'll write it down here because it's getting messy. Getting messy? All right, so what did I have? I had net F is mg sine theta minus Fs, but Fs I'm going to put bam equals ma, I think. It was just ma, right? Ma. All right. What are we almost? Almost done. Then we'll be happy. Therefore, by the transitive property, we're almost happy. All right. M's go. And I've got ba and ah, so I'll put them together. So I've got good sine theta equals ah plus ba. So I can factor out an ah, ba, b plus 1. And I have what we had at the beginning, A equals good sine theta over beta plus 1. That is that.